Welcome, and thanks for joining us today for today's webinar, which is titled Overcoming the Constraints of Conventional Activated Sludge Treatment. My name is Sarah Elger, and I'm the Director of Strategy and Marketing at Enviromix. I'm thrilled to have you all here with us today. But before I begin, I want to cover a couple of housekeeping items. You are all muted now, and you will be for the duration of the presentation. So if you have any questions, please use the Q&A feature, not the chat, and that's located at the bottom of your screen to send any questions that you may have throughout the presentation. There will be a short question and answer period at the end, assuming there is time. But if we don't get to all of your questions during the half hour we have together today, we will be sure to answer each of your questions via email after the presentation. We will be emailing certificates of attendance to all who attend this live webinar. So let's get started. Today, we will be focusing on 3 water resource recovery facilities and the real-life constraints that they are forced to live within every day. I think that you will find yourself relating with these facilities, as we have found that nearly every wastewater plant suffers from one or more of these issues. We will then go into detail about the FlexZone Adaptive Process Volume, which is the Enviromix solution for overcoming the constraints found with the conventional activated sludge solutions. We will then discuss how the FlexZone was used for each of the 3 facilities to produce real-life solutions to their problems. And finally, close out with a summary and open it up for questions. Our first plant today is in Michigan. This plant is a nitrification plant targeting an effluent ammonia of 1 milligram per liter. The influent enters the primary clarifiers before being split between 3 parallel activated sludge trains, each consisting of 3 passes. Note that the expansion over the years has resulted in different aeration basin sizes. The facility is designed and permitted for 10 MGD. However, typically only receives between 5 and 6 MGD. The aeration system and blowers, as they should be, are designed at the 10 MGD load. However, operating at nearly half of the design with the inability to take a train out of service results in excess capacity. This extra capacity results in excessive aeration and high dissolved oxygen concentrations in the aeration tank. This not only consumes unnecessary energy, but also can cause them issues with settling. During nitrification in plants with excess air and no ability to denitrify, alkalinity is depleted, pH drops, and nitrification rates tend to drop. And this impacts effluent quality. The second plant that we will look at is in Iowa. This plant is currently a nitrification-only plant with 3 parallel trains in operation. This facility is designed for 1.75 MGD. However, typically operates closer to 0.3 MGD at minimum flow conditions. During these low flow rates, they will take 1 train out of service, but they need to keep 2 trains online to handle the high flows that they receive during rain and snow melts. At times, this plant sees dissolved oxygen concentrations upwards of 5 milligrams per liter, which can result in excess energy consumption. The plant is currently approaching a new permitting phase that will include a total nitrogen limit of 15 milligrams per liter. The construction plans include adding an anoxic selector with internal recycle pumps. However, the high DO concentrations that they're currently seeing in the aeration tanks must be reduced in order for the denitrification process to work as it's intended. Our third plant today is a larger facility located in Wisconsin. This facility is looking at ways to modify operations to meet future nitrogen and phosphorus limits without additional tank volume. They have the benefit of having 2 treatment trains shown here that accept a fraction of the total flow to the plant, and they can operate them in parallel to compare operation and treatment objectives while evaluating a number of different scenarios. Both of these trains operate in an AO configuration with an anaerobic zone upstream of a long, narrow aeration train. The bottom train will be used as a control train, while the top train will be the demonstration train, And this facility will see flow, or this pair of trains will receive flows ranging from 3 to 10 MGD. This plant has a desire to operate at low dissolved oxygen concentrations to utilize embedded carbon to promote simultaneous nitrification and denitrification. Under low DO operation, it's likely that the airflows would fall below the minimum airflow rate per diffuser and the mixing limited thresholds. Additionally, the plant wants to protect the anaerobic selectors from residual DO and nitrates that are oftentimes found in the return activated sludge lines. Now, to introduce the FlexZone Adaptive Process Volume System, the solution for overcoming the constraints faced by nearly all conventional activated sludge plants. So, what is FlexZone and how does it work? Well, the FlexZone is a system, the FlexZone system is a subset or fraction of an aeration train that is strategically sized and located upstream of a dedicated aerobic volume. At 20-year design conditions, the volume that's occupied by both the FlexZone and the dedicated aerobic volume is the tank volume that's needed for the aerobic capacity. There is no additional tank volume. You will see that we are just utilizing the existing volume in a unique way whenever the conditions are not at this 20-year minimum temperature design. The FlexZone is designed specifically around changing conditions to optimize energy efficiency and process stability. The FlexZone includes a select number of independently controlled zones. In this example, there are 4 subzones within the FlexZone. Each subzone contains both diffused aeration and biomix compressed gas mixing. And each subzone can operate as mixing only, aeration only, or simultaneous mixing and aeration. Online instrumentation, located both within the FlexZone and the dedicated aerobic zone, is used to provide feedback for the control system, which adjusts the aeration intensity and turns mixing and aeration on and off. Upon first glance, it's easy to confuse the FlexZone with a traditional swing zone. However, I personally feel that there are a few key limitations of a swing zone. First, a swing zone is typically just a single zone, or in rare cases, 2 discrete zones in series. Second, a swing zone requires baffle walls if any type of mechanical mixing device is being used. The baffles are needed to overcome the limitations of point source mixing, which direct the motion of the liquid to keep the solids in suspension. Next, a swing zone can only operate as either mixing or aeration, on or off. And it cannot typically operate mixing and aeration simultaneously. My colleagues often hear me comparing a swing zone to a digital signal. It's non-continuous or discrete, A or B, mixing or aerating. However, a FlexZone offers a smooth, continuous analog signal by comparison. A FlexZone consists of multiple subzones, which can each be operated independently. It also requires no baffle walls. The unique bottom-up mixing technology of Biomix allows for this, combining complementary mixing patterns of diffused aeration and compressed gas mixing. The FlexZone provides the ideal combination of equipment for concurrent aeration and mixing operation, which is distinctly different from the aeration and mixing equipment used in traditional swing zones, which cannot operate simultaneously. We call this concurrent operation SynchroMix. SynchroMix also enables us to infinitely adjust the aeration intensity up and down to match the demand. When aeration in any subzone is turned down below the mixing limited thresholds, the mixing system is automatically enabled so that the aeration can turn down even more. And when aeration is no longer needed, the FlexZone allows for aeration to be suspended completely in one or more subzones. And it's brilliant if I do say so myself. The flexibility just allows a plant to be free from the constraints that they are used to. the constraints to be able to freely adjust the system up and down based on the changing conditions. So what are the changing conditions that would constitute the need to alter between low loading and peak loading conditions? Well, they are conditions that most plants that I have been to experience. First, there's the oftentimes dramatic difference between the loading that the plant experiences at startup compared to the 20 or 30-year design loading that is predicted for the future. This change is typically slow and experienced over long periods of time, resulting in years of constrained operations. Seasonal fluctuations are another condition that some plants experience. Many tourist towns experience high periods of demand, followed by much lower off-season flows. Closely related to seasonal fluctuations are temperature variations. Many regions, especially those of us up in the north, require an increased aerobic mass or volume as the water temperature declines, and a subsequent need for less aerobic mass or volume when temperatures increase. The final condition that I want to point out is diurnal fluctuations. These changes happen regularly over the course of a day and are especially dramatic or impactful for municipal plants with smaller collection systems. In the middle of the night, the flow and loading can be radically different compared to the peak of the day. The scenarios shown on the bottom here illustrate just one example of how this specific flex zone can respond to changing conditions. So what is this carbon management and embedded carbon that we keep talking about? I've heard these terms in the industry a lot more lately. Carbon management is the concept that wastewater influent is abundant in carbon like COD or BOD. And that carbon can be redirected and utilized throughout the plant for beneficial use. Carbon can be used to improve denitrification and to enhance biological phosphorus removal. Carbon management is the reason why all these examples you have seen so far may have seemed flipped on their head. When engineers are trying to account for low oxygen demand at the end of an aeration basin, they may often include supplemental mixing at the back end of the aeration basin. But at the end of the aeration basin, all the carbon has already been chewed up, and a lot of aeration energy was used in the process. Efficient use of embedded carbon includes a strategy on controlling or varying the biological reactor environments to improve biological nutrient removal before the carbon is consumed. In the example shown here, the flex zone with decoupled mixing and aeration equipment capitalizes on redirecting influent carbon in a low DO environment for simultaneous nitrification and denitrification, thus reducing the overall oxygen demand while protecting against recycled nitrate to the anaerobic zone. So what's included in the flex zone offering? The flex zone is a complete solution, including aeration, mixing, instrumentation, and controls, along with the design of the system. The flex zone is agnostic to process configurations and can enhance the performance of all process designs, anything from a nitrification-only plant, MLE, AO, Barden-Faux, just as a few examples. The solution includes a process design, which defines the volumetric requirement for the flex zone and the number of subzones along with the aeration and the mixing equipment needs. A plant can utilize an existing low-pressure air supply, or Enviromix can size and provide process blowers. Biomix is interlaced with the aeration grids to provide mixing as needed. The aeration grids must coincide with the biomix grids to define the individual subzones. Existing grids can be modified with additional drop legs, or new grids can be supplied. Modulating valves, airflow meters, and process instrumentation such as DO are provided within the flex zone and a dedicated aerobic zone to provide online feedback for the control philosophy that is contained within the master control panel. The control system is responsible for modifying the aeration intensity and turning on and off both the mixing and the aeration systems, while keeping the aeration efficiency and energy consumption front of mind. The following is an example of how the control system adjusts the operation of a flex zone throughout a diurnal cycle. In this example, the flex zone has 2 subzones and is targeting a DO set point of 2 milligrams per liter at the end of the aeration train, or that fixed aerobic zone. As the load fluctuates during the day, I want you to closely watch 2 different things that are going on within that aeration take drawing. First, I want you to pay attention to the mixing and the aeration bubble patterns in each of those 2 subzones. Right now, in the middle of the night, you can see that the first subzone is anoxic with only mixing in operation. And the second subzone is both mixing and aerating in a lower DO environment. The second thing that I want you to pay attention to is how the DO concentration in the flex zone adjusts up and down in response to the demand. The DO target in the flex zone will change, whereas the set point in the fixed aerobic zone will stay constant, ensuring complete treatment at the most efficient airflow rate. So, as we proceed through the day, you can now see that the load has increased during the morning, and the flex zone has responded by turning the air on in that first subzone, which was previously mix only. Additionally, you can see that the DO target in the flex zone has increased slightly to 0.8 milligrams per liter. Now, at this point in the day, the aeration demand has increased such that the airflow in the 2 subzones is greater than what the mixing limited threshold is. So the mixing equipment is shut off, conserving energy. Now both subzones are aerating and targeting an even higher DO concentration. As we reach the peak of the day, the target DO has further increased up to 1.5 milligrams per liter, matching the demand at this example plant that is operating already near the design loading conditions. As the load drops out later into the evening, the flex zone responds by dropping the target DO and again shutting off the aeration to the first subzone. I hope this example helped you understand a little bit more of the flexibility within the flex zone. Now, let's get back to those projects that we discussed at the start of this webinar. I will present each one individually and show you the flex zone solution that each plant is currently constructing. If you recall, the plant in Michigan had a number of constraints that they were looking to overcome. The plant is currently operating at about half of its design flow, but it's unable to reduce the aerobic volume in operation, which results in high DO concentrations in the aeration basins. This leads to higher energy costs than preferred and challenges with alkalinity consumption and settling. As illustrated with arrows on the bottom image, each aeration train is 3 passes. As we talk through the solution, we've extended those 3 passes out horizontally and depicted it as a single long aeration train. The flex zone in this project was strategically placed in the middle pass of each of these aeration trains. So the first pass remained aeration only, and the last pass remained aeration only. Enviromex worked closely with the consultant and the plant to create a design that resulted in the least amount of change to the existing equipment to ensure a quick installation timeline and most efficient use of the funds that they had available. The flex zone is divided up into 3 subzones, each of which can be independently controlled with its own mixing grid and aeration grid with automated valves. The aeration grids are all existing, and the only required change was to swap out the ceramic diffusers for membrane diffusers within the flex zone. The subzones will operate as mix only the majority of the time. This will provide a volume within the tank to denitrify, resulting in alkalinity recovery, oxygen credit, and energy savings. However, during winter months, when the water temperatures drop in Michigan, the plant will require more aerobic mass or volume, and as such, the flex zone will adapt to provide 1 or even more aerobic zones to ensure complete nitrification. Now, let's switch over to the plant in Iowa. If you recall, the plant was working through a design upgrade to address a new total nitrogen limit, and knew that they were battling high DO concentrations due to the low actual flow compared to the design. A part of the solution is the addition of some anoxic selectors, which are not shown in this aerial image. In order to ensure that high DO concentrations are not recirculated back to these new anoxic selectors, the plant and consultant wanted to be sure that we had the ultimate turndown capability within these 3 reactors. The resulting design included compressed gas mixing in the anoxic selectors, and then dividing up each of those square aeration tanks into 2 subzones, each one equipped with both mixing and aeration equipment. When matching the oxygen supply to the oxygen demand, the reactors have unlimited aeration turndown capability. The plant can operate one subzone with only aeration and the other with both mixing and aeration, or they can operate both subzones with both mixing and aeration. The status of the mixing being on or off will be controlled by the master control panel provided by Enviromix, which will modulate the automated valves to the process trains and also call for more or less air from the blower system. When the control system identifies mixing limited conditions, the mixing equipment will be activated. This control strategy will allow and ensure that the anoxic environment is protected from high DO return streams, and will allow the operations and maintenance staff to focus their attention away from any manual adjustments to this process and on to more important and pressing matters that they may have at the facility. And last, but certainly not least, we return to the Wisconsin plant. If you recall, this plant was running a demonstration comparison on 2 parallel trains. The evaluation will support in identifying a way to meet future nitrogen and phosphorus permits utilizing the existing infrastructure. Enviromix is pleased to be partnering with the plant and their consultant of record to complete this expected 2-year evaluation. The long, narrow trains are shortened up here so that it's big enough to visually see the different portions of the reactor. The existing anaerobic zones are shown. The fact that there are 2 zones will be an important distinction in just a moment. The plant has exchanged vertical entry mixers with Biomix DC for enhanced fermentation in those anaerobic zones. That gives them the ability to generate volatile fatty acids to help stabilize BioP. The remaining portion of the aeration train is divided up with over 65% of the reactor modified as a flex zone. The size of the flex zone was determined by working around existing aeration grids while also considering the fluctuations in flow and load that are to be expected. During the first phase of testing, the focus will be operating the flex zone in low DO environments to facilitate simultaneous nitrification and denitrification. Operating in this fashion will ensure efficient use of the embedded carbon that's coming into the influent, while providing denitrification to protect that anaerobic zone from high nitrates in the RAS stream. The aerobic volume will be expanded during high loading periods by increasing aeration capacity to 1, 2, or even more of the subzones, ensuring that nitrification and BOD removal is not impacted at peak load. We will also be testing the SNDN evaluation against a more traditional A2O process configuration. For this evaluation, the plant is in the process of installing an internal recirculation pump with piping to the formerly second anaerobic zone, converting that into an anoxic zone. In this configuration, the flex zone will be adjusted between mixing only, low DO, and aerobic environments, depending on specific goals and loading. When the front subzones in the flex zone are operated as mix only, it effectively expands that anoxic zone, allowing for reduced IR pumping rates. When the subzones are operated in low DO environments, carbon will be utilized for denitrification instead of treating carbon with aerobic environments. Reducing the carbon load on the aerobic zone is expected to improve settling. Finally, any or all of the subzones can be adjusted to aerobic conditions when loading is high an additional aerobic mass or volume is required, instead of increasing mixed liquor concentrations. I hope that you enjoyed this presentation and have thought of at least one example where FlexZone can benefit your plant or a plant you are designing or upgrading. We just covered a lot of material, so how about if I summarize before I open it up for questions? When we think about overcoming the constraints of conventional activated sludge, it's important to focus on a few themes that we identified between these three plants. Of course, there are always going to be attributes that are unique to each facility or application, but let's just start with the basics of what to look for. The FlexZone system is ideal for plants struggling with constraints such as aeration and blower control limitations, whether that be the inability to turn off existing aeration grids or tanks or limited aeration turndown. The FlexZone is ideal for plants struggling with nutrient removal and carbon utilization, whether that be with future tighter limits coming up or struggling to protect the integrity of anaerobic or anoxic zones. The FlexZone is perfectly suited for plants with constraints such as load fluctuations, whether that be startup versus design, seasonal changes, or diurnal peaks and troughs. And the FlexZone is ideal for plants struggling to manage all of the above within their existing infrastructure limitations. The FlexZone overcomes these constraints by providing multiple independent subzones that allow for concurrent aeration and mixing, therefore eliminating mixing limited conditions. The system provides responsive process environments within each of these subzones that can be operated as aerobic, anoxic, or low DO environments, utilizing that embedded carbon more effectively and efficiently. FlexZone also provides dynamic automation and controls to quickly adapt to changing load conditions. And finally, FlexZone provides versatile configurations with independent mixing and aeration designed around existing tank and diffuser grid layouts and working with existing blower configurations when possible. The FlexZone also provides versatility in new construction design, especially when considering how to design for the needs of tomorrow while addressing the constraints of today. That concludes our webinar. Thank you for your time and your attention. I will take a look through any questions that were submitted via the Q&A feature. Any questions that I don't get to during this live webinar will be answered via email by either myself or by another member of our great team. As I said earlier, a follow-up email will be sent to all participants with a certificate of completion. When you exit out of this webinar, please take a moment to complete the short survey that will provide us feedback and let us know if you would like someone to contact you about any of our Enviromix products. Thank you so much, and I hope you are just excited about FlexZone as I am. All right. I do see a few questions in here, and we do have just a couple minutes before the half hour is up. One of the first questions is, are DO probes the only probes that are used for this process control, or are there any other probes that are used? The core base control is based on DO sensors, mostly because we know that most plants like the maintenance regards around DO probes, and they're easy to maintain. They're very accurate sensors. We do offer other control philosophies, such as like an ammonia-based aeration control strategy or a nitrate control strategy. However, we want to make sure that those plants that are interested in that philosophy understand the maintenance and calibration requirements required with those types of sensors. So we do have some advanced control philosophies, but the standard base offering was specifically designed around DO sensors. I have another question here that's asking if you can retrofit this equipment for an existing oxidation ditch. Yes, we can do that by extending out the oxidation ditch into kind of a long, not serpentine, but wrapping around the ditch aeration train, so it's like a pass, and we have worked on projects like that in the past before. And then there's some questions around potential for energy savings. Absolutely. We have energy calculations that we can prepare for any plant that's interested in looking at how this design would fit into their system and what their energy savings would be now or as the load increases throughout the life of the facility. Obviously, anytime where you're able to reduce that aeration demand to match what's right now and be able to actually turn off large sections of the aeration grids or the aerobic tank, you're going to see substantial energy savings. Some of our customers have upwards of 70% of the aeration tank that isn't actually needed and is considered mixing limited. So there's some really substantial energy savings with that. I did notice that I just went a little bit over, and I do see plenty of other questions here. I appreciate all of your questions. We will get those answered to you and send you out emails with regard to that. Please feel free to submit any more or contact me at my email that's listed here. In respect of all of your time, I will close out the webinar, but thank you so much for your time, and I look forward to hearing from you soon. Have a great day.